Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everyone. We're kind of past the legal 5 minutes, so I think we should start. It's a great pleasure for me to introduce our visiting speaker today, Professor Peter Vary. And looking at the audience, and most probably knowing who is going eventually to watch us online, it is needless to tell who Professor Vary is. I will just finish the introduction with his current job title. He is the director of the Institute for, okay, let me find it, the Digital Signal
Communication systems.
Okay, the Institute of Communication Systems and Data Processing in RTWTH Aachen University. Without further ado, Peter, you have the floor.
Yeah, thank you very much, Ivan, for inviting me, and hello to all of you. It's now, in 2013, 20 years, then we had the first true digital mobiles in commercial GSM networks. And one of the first mobile was the Motorola 3200. I don't know how the name was chosen, but that was approximately the price in Deutschmark. And the weight was 580 grams. And during the first years of GSM, I would say the main focus was on reducing the size and increasing the talk time of the mobiles. And in the second 10 years, we saw that the computational capacity of the mobiles was increasing so much that we could do other things, just like having a phone call. We had the cameras, we had the calendar, and we had the apps. Nowadays, it's not a mobile phone anymore, or let me say mainly it's a mobile computer, it's a mobile apps computer, and the price is not really what you pay in Germany. That's a matter of advertisement of the companies. But the weight is about 110 grams, so a reduction in size and in weight, and a dramatic increase in terms of complexity and capabilities. And now the question arises, what can we do to improve in the future? And there are different approaches. One is, I would say, the distinguished British approach by the company Virtue, which is connected to Nokia, very precious devices, or an alternative solution from an Austrian designer jeweler, the King's Bottom iPhone. But that's not what I would like to talk about. Then I said we have now 20 years of mobile phones. We have seen that it's still a phone. You can still use it as a phone. But during the last 10 years, we have not seen too much progress in terms of speech quality. And that's the topic of my talk, the path towards high-definition telephony. So let's see what is high-definition telephony. I would go through some issues like speech coding as such, and HD voice and model-based bandwidth extension. That might be an important keyword. I will address error correction and have some ideas about a future step at the end. Now we have the plain old telephone system, which is due to history. In the old analog days, the capacity of long-haul range transmission links required narrow frequency band per channel. And this is why we have this old limitation to the telephone bandwidth, which is 300 Hertz to 3.4 kilohertz. And we know how to use the telephone, but actually the intelligibility of syllables is only 91%. That is not too much. And quite some often we need a spelling alphabet on the telephone because we don't get the right syllables. HD voice is at least 7 kilohertz, but We include also the lower frequencies down to 50 Hertz. The technical term is wideband, but the marketing people invented the term HD, so everyone understands what it is. And here we see the bandwidth, which is increased significantly, but there's even more than wideband. There is also super wideband, up to 14 kilohertz. So the low frequencies increase naturalness and comfort, because the fundamental frequency of speech is mostly not transmitted on the telephone. And if we include that, it sounds more natural, and you can distinguish between the daughter and the mother on the telephone. That might sometimes be important. The higher frequencies contribute to clarity and intelligibility, and if we increase even further, we can improve brilliance and quality of music. Quite often, only the minor part of the speech spectrum is transmitted. This is the telephone band. This is an unvoiced sound, and we see even more energies beyond the telephone band. And if we include that in terms of wideband or HD coding, we will significantly improve the quality and the intelligibility of syllables. So we have these categories: narrowband, wideband, super wideband, sometimes it's called HD+, and full band, if that is needed, or as a reference. Now I would like to address speech coding, or more and more we are talking about speech audio coding, speech audio signal processing, and but for the time being in the mobile phones we have pure speech coding, and the simplified explanation of what is a mobile phone about is given here. There's a model of the speech production mechanism of the vocal tract. We have the vocal folds and we have the vocal tract, and that can be described by a model where we have a generator and a filter, time-varying filter, and this is what we see at the receiving end in the mobile. There is the model of speech production that is implemented, and over the air we transmit the parameters which are needed to drive the model, and at the transmit side we extract from the speech the model parameters. So actually it's some kind of naturally sounding vocoder what we are using there, but it is more and more a mixture of parametric coding and waveform coding. The most important codecs we have in the GSM mobiles is the very old full rate codec from 1988. It was very simple, and then we had improvement in terms of technology. The microelectronics became more powerful, and 10 years later we have what is called the adaptive multi-rate codec, and later on we have had to add the term NB, narrowband. So it's telephone bandwidth, the sampling rate is 8 kilohertz, it's much more complex, and it has different bit rates. It goes down to 4.75, and the maximum bit rate is 12.2. That is the codec which is preferably used in the mobile phones. That's also called the enhanced full rate codec, 12.2 kilobits per second, and it's based on the model of speech production in terms of code-excited linear prediction. We have here two stages of the filter: the vocal tract, the vocal folds, the gain, and some excitation generator, which is a vector codebook, and what is transmitted over the channel is the vector address. Typically it is 40 samples, that is 5 milliseconds, a gain factor that is filtered to produce 40 samples. So that seems to be very simple. The secret is how to extract at the transmit side the best vectors, the gains, the coefficients, such that we can code it with a very low bit rate and still get excellent quality at the receiving end. The motivation for designing the adaptive multi-rate codec was not to improve the quality. The motivation behind that was usually we have a full rate channel in GSM that is 22.8 kilobits per second, including source coding and error protection. And if we can keep that rate and reduce the bit rate for speech coding, we can increase the number of bits for error protection. And that's what's happened with the AMR codec. If you have a full rate codec, the bitrate is always 22.8. If the mobile is outside, we use the enhanced full rate codec, highest bitrate, highest quality. If a channel gets worse, maybe that the mobile is inside a building, then the channel gets bad and we increase dramatically the error protection and have still a reasonable quality. But the quality it will never be better than if we use the highest bitrate. So the motivation and the objective of the AMR narrowband codec is to save money from the point of view of the operators. Because if you would like to improve the in-house coverage, you could install more base stations outside the building, inside the building. So it's a reasonable and a good solution at that time to improve the service quality in the mobile networks by introducing the adaptive multi-rate codec. And it can switch very quickly between the different bit rates every 40 milliseconds. If there's a half-rate channel where the bit rate is just half of that, I will not go more into the details. Now we have seen high definition is at least 7 kilohertz, and there are some examples like Skype, and I guess this is the first time users became aware that telephone could be more than just the telephone quality. There is voice over IP, the Opus codec. I should add here the Windows Live messaging system and others. And we see there is already standardization very, very long ago. In 1985, we designed the first wideband codec, the ITU standard for ISDN. It was designed for ISDN networks to increase this quality, and now the patents are not valid anymore, and we see the first products. And one of the products is called DECT Plus. That's the digital cordless telephone, and it is used in combination with a SIP protocol over the internet. But it's difficult to use. The normal customers, I'm sure, will not use that because you have to combine the telephone with a router and to have installed software, and you have to know someone who has it. So it's by far from being a standard in the fixed network so far. Then we have in the 3GPP domain what is called the AMR wideband. That's the next standard, adaptive multi-rate wideband standard. Interestingly, it was ready in 2001, more than 12 years ago. It was designed, at that time we had no third generation and no fourth generation. It was designed for GSM. It could be used in GSM. It was never used in GSM. And there are some activities to introduce that in 3G and in 4G mobile networks. But there are, for quite some while, there are some mobiles on the market which have the AMR wideband, and it is used but only for the ringing tones, not for the communication. But that might change. Now let's try to get some idea about the quality. This is narrowband quality, the standard quality in GSM.
Slow-cooked hippopotamus in red wine. A recipe for special occasions, provided that the hippopotamus feels comfortable in red wine.
Now,
slow-cooked hippopotamus in red wine. A recipe for special occasions, provided that the hippopotamus feels comfortable in red wine.
Now, the question is, well, this is a significant improvement, but could we do more? So, does it make any sense to improve in terms of bandwidth for speech? So, let's listen to 7 kilohertz wideband.
Slow-cooked hippopotamus in red wine. A recipe for special occasions. Slow-cooked hippopotamus in red wine. A recipe for special occasions, provided that the hippopotamus feels comfortable in red wine.
And clearly, the naturalness increases and the transparency even more. But we have not only speech, we also have music. Let's listen to GSM and music. So we could even in the mobile networks transmit audio quality. There are some codecs to do that. And the bit rates are such that we can transport them in the 3G networks. There is only packet transmission. In the 4G networks, LTE, we have packet transmission, so there would be no problem to introduce that in principle. The objective of the AMR wideband codec is to increase quality and intelligibility for the first time. And interestingly, the bit rates go down according to the AMR principle to 6.6 kilobits per second. Then it can be filled up by error protection. The quality is not as good at 6.6 as at 24 kilobits per second. If you try to find out where in the world is HD voice, you find the Global Mobile Suppliers Association, and they keep track of the announcements of the operators. And the latest count is that there is HD voice launched or announced in 61 mobile networks, mostly 3G, in 35 countries in the world. If we look to Germany, it's not that clear. We have a pretty good coverage for 3G and 4G for the two main operators. It looks very similar. And all of them are saying, we have HD voice, but if you go to the shop, no one can tell you how to use that because it's partly installed in the network. It's not everywhere because we have different suppliers for the infrastructure, and it's obviously a strong effort to implement HD voice in the network. In some countries we have it live, like in France. In UK there are several networks, 3G networks, which offer HD voice, and meanwhile we have plenty of mobile devices which can do that. And this causes the next problem, interesting problem for the speech processing community. If we install HD voice in the network, we have to modify quite a lot. To give you an example, a German-wide coverage of GSM requires about 19,000 base stations. And if you install such a new codec, you need a new speech codec and you need a new channel codec. In the mobiles, that's not an issue because you buy a new mobile, but the base station is there and you just need a software update at the base station. But it's like with the PCs. If you ever tried to update your PC, which is 10 years old, to install the latest software, there might be some problems. So it's more than trivial to introduce HD voice in the network because you need a lot of modifications and protocols. The coding part is installed in the mobile switching center. You don't have so many, that's not so critical, but the base stations is the point. And if you have done that, you have two separate worlds. The customer buys a new mobile and he knows, hopefully, a few friends who also have the HD service, but there is no cross connection in terms of quality between a narrowband and a wideband terminal. And it will take quite a very, very long time until, or if ever, the whole telephone network has been converted to HD voice. And then we can study all kinds of interconnections between HD and narrowband mobiles over HD and narrowband networks, for example, to such a guy who has the new HD mobile phone. So if he is happy, we have the complete chain in HD, but if the user at the other end is narrowband, he gets only narrowband quality, even if the user here is connected via a 3G network. That could be 3G LTE, that could be GSM, then it can take profit of the HD capabilities because it transmits only narrowband noise and narrowband speech. Then it might be that the HD terminal is connected to a narrowband network, then they also have only narrowband quality, and so we have different solutions. Now I would like to studied these cases. The case A is the happy case where we use the AMR wideband codec or the AMR wideband plus codec. Then in this situation we try to improve. We could try to improve by, the key word is now bandwidth extension. We transmit just the narrowband signal, and in the mobile we try to exploit the model of speech production and some characteristics of the human ear to artificially increase the quality or eventually the intelligibility. From an information theoretical point of view, that's very questionable, but we have here a specific source and we have a model and we can do something. I will demonstrate that. If the mobile, the narrowband mobile, is connected via the 3G network, we could also implement this artificial bandwidth extension in the network. Therefore, I'm saying it's two cases, B1 and B2. It doesn't make a big difference. The question is, where is the processing power? If we have only the narrowband network but two HD terminals, it seems to be that we can do nothing, but we can do something if we succeed to transmit in a compatible way side information for artificial bandwidth extension. Well, we could use, as in the first case, B1 artificial bandwidth extension at the receiving end, but the quality improvement is limited. As soon as we can transmit additional side information which drives the bandwidth extension, the quality becomes much more better. Some of the codecs have the element of artificial wideband extension as part of the standard already. So the idea is the narrowband network, let's say, transports only PCM or an AMR narrowband codec, and we embed some information. We will see how to do that. And we try to do that in a compatible way such that a narrowband terminal gets narrowband quality and will not be disturbed by the embedded information, which can be used by the HD terminal to expand the bandwidth. The first case, just receiver-based, that was scenario B1 or B2, where the bandwidth extension is in the network. It tries to estimate some characteristics of the speech and to expand the speech artificially. It's a mixture of speech recognition, of estimation, and speech synthesis. And in listening tests, I can tell you the listeners clearly prefer artificial bandwidth extension. And in certain occasions, if you have background noise, artificial bandwidth extension even increase intelligibility. One approach of my former PhD student, Peter Jax, was purely based on linear predictive coding. What we are doing here, we receive a narrowband speech. Let's say that's already decoded. It's PCM. And the first step is to interpolate from 8 to 16 kilohertz. Then we apply a pattern recognition approach where we extract some features. We have a statistical model. The goal is to estimate the spectral envelope of the wideband speech. So at the end, the wideband speech will be reconstructed by applying a wideband synthesis filter. And the goal is to estimate from parameters which are extracted from the narrowband signal the envelope of the wideband signal. And it uses a codebook. The codebook could be, for example, just the LPC or the LSF quantization codebook for the LPC information. It uses bias estimation. And what we get is the LPC or reflection coefficients or capsule coefficients of the wideband filter, and we apply the analysis filter to the oversampled narrowband speech. What we get is the oversampled residual signal. And if the signal was limited to 3.4 kilohertz, the residual will also be limited to 3.4 kilohertz. If the prediction goes quite well, and let's say if the voice was unvoiced, we have a flat noise spectrum up to 3.4 kilohertz. but we need it up to 7 kilohertz. So it's not too difficult to imagine how to expand the narrowband flat noise to a wider flat noise, just by spectral replication or spectral translation. If the speech is voiced, then we have here a harmonic narrowband noise with more or less constant spectral components. It has a harmonic structure, and it's not too difficult to imagine how to expand that to a wideband excitation by spectral repetition, folding, modulation, whatsoever. I can tell you the extension of the excitation signal is very easy, and it's not critical at all. The art of bandwidth extension is how to estimate the envelope. And then we can apply this wideband excitation to a wideband synthesis filter and get hopefully decent quality. So this is a little bit about the theory. You get some idea that is pattern recognition and conditional estimation. I will not go through the details, and would like to play one example. What we see here is a spectrogram, and it switches between narrowband and the artificially extended signal.
Well, 3 or 4 months run along, and it was well into the winter now. I had been to school most all the time and could spell and read and write just a little, and could say the multiplication table up to 6 times 7 is 35. And I don't reckon I could ever get any further than that if I was to live forever. I don't take no stock in mathematics anyway.
So the quality is significantly better, and if there is some background noise, tests indicate that even the intelligibility is increased. The second approach for artificial wideband extension is to embed information, to hide information in a compatible way in the bit stream. That was the scenario C, and we will see here 2 different versions how to implement that. We add some side information. So we transmit a narrowband bit stream or narrowband speech samples over a narrowband telephone network. The normal narrowband terminal should not be confused by this hidden information. And the bit format, the stream, the frames, and all that should be the same as before. Or let me say at least according to the specified formats. And the HD terminal could extract the hidden information to do much better bandwidth extension with the transmitted side information. No increase of the bit rate, no modification of the bit stream format. And I would like to discuss this with an alternative version, how to expand the bandwidth. The first one was to use purely LPC-based techniques, LPC analysis, filter, expansion, and synthesis. The second one is to split the signal, the wideband signal, into a lower and an upper band. So subband processing, we need not to do anything with a low-pass band, but we try to resynthesize at the receiver the upper band, the high band, from 4 to 7 or 8 kilohertz. But the bit stream is according to a narrowband signal. What we have here is the baseband decoder, let's say the AMR narrowband codec at 12.2 kilobits per second. We get the narrowband signal. It's sampled at 8 kilohertz. We have a filter bank, a 2-channel filter bank, which does the interpolation job to obtain the enhanced signal sampled at 16 kilohertz. And here's the extension band synthesis, and the first approach is to hide data by watermarking techniques or steganography in the bit stream. For example, 2 kilobits per second, that's quite a lot, but we don't need so much for wideband extension, or not much more. To extract some parameters to do here the bandwidth extension, and I would like to explain that once more using the AMR codec, the simplified block diagram here, the vector codebook, the gain factors, and this filter which has 2 stages as we have seen before. But the point is to exploit the properties of the vector codebook or the vector search. Without going too far into the details, I can say that at the transmit side, finding the best vector is done by a procedure which is code, excited linear prediction, or which is called analysis by synthesis, or you could also say trial and error, because you try out which is the best excitation, and there are many, many different approaches how to design a codebook, and there are few approaches how to design a search procedure in a codebook which is, let me say, specified by the 3-kind search. It's not, it is not a codebook which is stored, but it's constructed iteratively by some search procedure. And this is the optimization criterion. H is the matrix where we have the impulse response of the synthesis filter. The vectors have a length of 40, that is 5 milliseconds, and this has to be optimized. And in the standards there is, for complexity reasons, a non-exhaustive search, because in any case the codebooks are very, very sparse. The dimension is 40, and typically the number of codebook entries is 2 to the power of 10, 1,000 roughly. Here the dimensions is only 2, and in the codebook we have here obviously only 4 entries to explain the principle. So a sparse codebook, and the first idea to use watermarking techniques could be to split the codebook into 2 different codebooks. No, that's too fast. A codebook to use, to split the codebook such that we, let's say, use the green codebook either or the red codebook. We just separate in 2 codebooks, and the hidden information is 1 bit. If we use the green one, the bit is 0, and if we use the red one, the bit is 1. And the receiver can find out which entries have been used, and he knows the information which has been transmitted. The disadvantage is that the quantization error increases because we have reduced the size of the codebook. But as the codebook is that sparse, we can invent a second codebook of the same size. And then we have no loss in terms of quantization errors, and the receiver knows if the red or the green book is used, which bit is transmitted, which polarity or sign of the bit is transmitted. Now, and this can be implemented in a modified non-exhaustive search, because if we study the AMR codec, we see there are at least 1,000 possibilities to specify a codebook of size 1,000. 1,000, or let me say 2 to the power of 10, means we can hide 10 bits in the codebook address of a vector of length 40. And as 40 samples is 5 milliseconds, that is 2 kilobits per second. So this information is used to drive the bandwidth extension at the receiver, and here it's the subband approach. The high band signal is here produced by controlling the time envelope, by controlling the frequency envelope, by controlling the excitation generator, which produces noise or some periodic signal. And the bit stream is extracted in the decoder in the part where the codebook address is decoded to find out is it red or green. So we have 1024 different colors, and the color says which is the 10 bits which are just transmitted. So I explained that already, and let's study some example. This is narrowband speech, and this is extended speech with the side information of 1.65 kilobits per second. We have taken this because this was, as indicated somewhere, became part of the standard of the extension of the G729.1 codec, where Bernd Geiser designed this solution, and which, including channel coding 2 kilobits per second, the bandwidth is extended from narrowband to wideband, and he used that module to expand the AMR codec, but hiding the bit stream in a compatible way. Now let's listen to one example. The first test is to which extent gets a conventional mobile, narrowband mobile confused or disturbed. Do the listeners recognize that there is something which has been modified in the background?
He suffered terribly from a speech defect. He suffered terribly from a speech defect.
Faulty installation can be blamed for this. Faulty installation can be blamed for this.
And actually, you don't recognize the modifications. Only the very experienced listeners sometimes can distinguish there might be something different. So it would be allowed to do that. And then we can embed the 2 kilobits in the bit stream of the AMR codec. And we can compare the narrowband receive terminal and the wideband receiving terminal in terms of quality.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so. To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
And that sounds much better, or significantly better, than the artificially expanded signal where we don't have site information at all. But the drawback of that solution is we have to transmit the bit stream as it is. As soon as we have transcoding in between, let's say a call from a mobile to a different network, and if there is PCM, for example, in between, the hidden information gets lost. But if a transmission is tandem-free, which is one of the options in GSM, then it would work. And the nice idea would be the operator just has to sell to 2 people 2 mobile phones without modifying the network at all. If they are in the same network, they would, from the very first usage of a telephone, have wideband quality. But there is a second solution. And the second solution is to avoid this tandem problem and to hide the signal in the samples, not in the bit stream. And the idea is just the following. Here we have the wideband spectrum, and we take the spectrum from 4 kilohertz to 6.4 for a certain reason. And we compress this and place this in the gap between 3.4 and 4 kilohertz. If you have a narrowband signal and if you have clean telephone band passes, the stop band frequency of the band pass is 3.4 kilohertz. And between 3.4 and 4, we can transmit something else. So in-band signaling, but in-band compressed transmission of frequencies here. If it is periodic, it will be compressed, and you could also say it's pitch scaling or spectral compression. And we do that in the frequency domain. The detailed solution will be explained next week by Bernd Geiser at the ICASP. The processing is based on DFT domain. We have a first analysis with a large window and a second analysis of a high band signal. First of all, we split the signal into a high band and into a low band. We decimate the sample rate from 16 to 8 kilohertz. And then we have here a short analysis and here a longer analysis. And we inject this spectrum in the high band. We do resynthesis, and there's more windowing and overlap to obtain wideband speech. This is the wideband signal. And we clearly see that there's a lot of energy here, especially in unvoiced sounds. and there is less energy in the voiced regions. So if we do compression here and it is more or less noise-like, we can expect it's not so critical because we don't have too many harmonics here. This is the high band. We take this and we compress it and place it in the range between 3.4 and 4. I said we take the high band from 4 to 6.4 and we compress it by a factor of 4, so we can place it here in this gap, which has a width of 600 Hertz. This is the narrowband signal where we did not apply the telephone bandpass. You see in the true speech it goes up to here, but here would be the 3.4 kilohertz limit here, and we will replace this, as you see, and it looks different. I go back and forth. It looks different, but even if you listen to that, it doesn't sound too disturbing.
Oak is strong and also gives shade. Cats and dogs each hate the other.
But the normal terminal would have some telephone bandpass and would not allow to offer these components to the user. But what we see is the insertion of the fricative sounds. This is a comparison of the reconstructed wideband approximation and the original wideband signal. The original wideband signal does not have here a gap between 3.4 and 4 kilohertz, so that's the true wideband. The narrowband signal has a gap because there's a cutoff frequency at 3.4 kilohertz, and we replace the high band here, and the gap is not annoying at all. We know that from different codecs that you will not hear the gap, and therefore we can expect a good quality. So let's listen to the extended.
Oak is strong and also gives shade. Cats and dogs each hate the other.
And the uncoded.
And dogs each hate the other.
Oh, sorry. I repeat it once more because
Oak is strong and also gives shade. Cats and dogs each hate the other. Oak is strong and also gives shade. Cats and dogs each hate the other.
It might be that you can recognize slight differences, but usually you don't have the A-B comparison and the quality is pretty good. Now we have different options to improve the quality in the networks by coding, better source coding, compression, hiding information whatsoever. But then we have a transmission channel with errors. The question is, can we keep the quality even if we have bit errors? So we have to study the bit error sensitivities, and maybe we have to use all the tricks which are known from channel coding. And one interesting solution is turbo coding, because you can just apply it at the receive side. And a very special, interesting solution is, we call that turbo error concealment. So that is the idea of turbo coding applied to a channel decoder and a source decoder. Usually a turbo decoder has two component decoders. One helps the other in an iterative procedure. And this concept can be applied to a channel decoder and a source decoder, or let me say a parameter decoder. I will explain that. This is the transmission model we have at the transmit side. We extract some parameters, let's say any codec. We have channel coding, we have modulation and transmission, and at the receive end we have a soft in, soft output channel decoder. No real turbo decoder so far, but just soft in, soft out. It's a component of a turbo decoder because it can accept extrinsic information. Extrinsic information means, what do the other bits know about me as a bit? The processing is as follows. The soft out channel decoder produces bits and it produces reliabilities. The reliability is saying which is the probability that the bit here is 1 is right or wrong, and usually it's described by the log likelihood values. And then we calculate here so-called a posteriori probabilities, not on bit level but on parameter level, because what we extracted here is parameters, LPC coefficients, vector addresses, gain factors. And these still have some redundancy. If you study the first LPC coefficient in a sequence, you will see there is clearly correlation. If you study the prediction signal of a predictive coder, and even if you have perfect prediction, you would say, well, the output is white noise. Even in white noise, we have still redundancy, because the white noise, even if it has no correlation, has a certain distribution, usually Gaussian distribution. And that is still redundancy. Redundancy on the level of the samples or on the level of the parameters. And this is extracted here in this block. This simple equation describes at the end what happens. We calculate a posteriori probabilities. We give something back on bit level. I will explain that on the next slide. So there is some iteration between the soft channel decoder and the first block of the soft decision source decoder. And after stopping the iterations, we know the best a posteriori probabilities. So that means we have, let's say, a parameter v, and the parameter v might be transported by 3 bits. So if it is 3 bits, we have 8 possibilities. At the transmitter, there is a quantization table, if it is scalar quantization, with 8 entries. So these are the entries in the codebook, and these are the 8 a posteriori probabilities which you have found after iterating here. So we have received 3 bits, and we are interested in the probability if x, let's say a group of 3 bit is fixed, which is the probability for the first, the second, the third, entry number 8. And then we do conditional estimation in terms of minimizing the mean squared estimation error, and it turns out we just have to multiply the codebook entries with their a posteriori probabilities. If the transmission is perfect, if there is no bit error anymore because the channel decoder has repaired all the bit errors, then only one of these probabilities will be 1 and all the others will be 0. So the summation does just the table lookup and is exactly compatible with the standard. If the transmission is completely disturbed, let's say only random bits, then it will turn out that the a posteriori probabilities have all the same value, 1 over q or 1 over 8, and what we get is the average of the codebook entries. And if that was a parameter with a sign and a symmetrical distribution, the average will be 0. So we have graceful degradation. So that improves significantly the quality by exploiting residual redundancy on the parameter level, that is the distribution and the correlation of parameters. And from that we can feed back extrinsic information on bit level to the source decoder. Let's assume we have a situation with 3 bits and the channel decoder finds out that bit number 2 and 3 are 0 and 1, or should be 0 and 1 in one iteration, and the channel decoder asks the source decoder, what do you think about bit number 1? And the source decoder says, well, these 3 bits are belonging to a parameter which has a certain distribution which is known, and we know the bit assignment in the quantization table. So if the bit 2 and 3 are 0 and 1, we have 2 possibilities, obviously, that the first bit is 1 or 0, but this probability is larger than this here. And then we can take the quotient and the logarithm, and this is the language the channel decoder understands. That's the log likelihood value, which is fed back to the channel decoder. And in this way, we do iterations across the channel and the source decoder. And the improvements are quite impressive. This is table lookup decoding. This is source decoding. If we rate over the channel quality as a quality measure, the parameter SNR, not the speech or audio SNR, we take the parameter SNR of a gain factor, of the parameter SNR of an LPC coefficient. And if we do the iterations, we come very close to the theoretical limits, using the turbo-like process applied to channel and source decoding. One example, let's take speech. One iteration means actually no iteration. We just have one path through the decoder.
To further his prestige, he occasionally reads the Wall Street Journal.
2 iterations.
To further his prestige, he occasionally reads the Wall Street Journal. To further his prestige, he occasionally reads the Wall Street Journal. To further his prestige, he occasionally reads the Wall Street Journal.
Or let's listen to music. Yeah, so we, let me say, have solved the problem. We have good codecs, we have good ideas to hide information, and we have very powerful channel decoders. Then the question is, what might be next, the next step? Well, this is just one statement. It could be binaural telephony. And then we would need stereo headsets, stereo coding, and transmission. And you might ask, what is it good for? One situation I think you could imagine is you would not like, or you cannot travel to a meeting, and you would like to participate in the meeting such that in the meeting, instead of you, there is a dummy head, or at least 2 microphones, and we have 2-channel transmission, and you are in the environment B with a mobile, and you can listen and get spatial information. And for example, the environment A would be the meeting room at the airport, and the environment B is at the beach, for example. And we have produced a nice demo, and you see it makes really fun to participate in such a binaural audio conference. If you listen to that here by headphones, you get some idea which information you transmit. I would say it's just the opposite philosophy of what we are doing today. Today we try to suppress the background and the background noise and the acoustic atmosphere. Here we do the opposite and we transmit it. But the audio bandwidth is more than just telephone bandwidth. And it makes really fun if you apply that to groups. In that case, we have a group A and a group B, and only in each group one has a master headset with 2 microphones, and all the others have the headphones. The connection here might be wireless, and then everyone can talk to everyone. Ivan, maybe you attended our demo at the last iBank. It's very amazing. You look to the left and see, oh, he's not here in my room, he's somewhere else. And this might get a great acceptance, not only for the professional application of the audio conference, but even for groups of young people. Now, my conclusions is that mobile phones will, I would say, hopefully surpass the speech quality of fixed line telephones, because all the ingredients are there to improve the quality. We have the standards, and the networks provide sufficient capacity to transmit that, and it will become easier to introduce new codecs, because in the 3G and 4G networks there is no dedicated speech transmission mode, because it's just packet transmission, and then it will be much easier. But nevertheless, even in the new world of the 4G networks, we still have the old-fashioned old telephone network, and we have interaction of new and old mobile phones. And then we have a compatibility problem. Even if it seems to be that in quite a lot of networks there is HD voice on the move, I would say. You have to distinguish between announcement and real public use. But then we will see the discrepancy between narrowband and wideband, and in that situation, bandwidth extension might help to improve the user acceptance. Someone who is buying a new mobile phone can get some improvement from the very beginning, independent of the situation which is in the connection presently. And it could bridge the gap between narrowband and HD. And that could be improved significantly if we hide information, if we do the transmission in a compatible way, let me say over GSM or UMTS network, or eventually just a latest proposal to do frequency compression. And my impression is that could be a shortcut to HD mobile telephony. But the real step could be the future binaural HD telephony as close as being there. Yeah, that's the end of my talk, but I would like to cite some ideas, 2 statements about what is HD. There is one of an analyst, he says, the expectation for quality in the public on cell phones is so low, people say it's good enough. But there's on the other side the mobile manufacturer, Peter Eisberg, he said, it will be the most significant quality upgrade in telephone history. And I expect it will be something in between, but hopefully much closer to the most important quality upgrade. Thank you very much.
Questions there, colleagues?
I'm curious if you've tried some of the those demonstrations with the bandwidth extension in different signal to noise ratios and different noise settings. I was curious to hear if you have the demo how it actually sounds in 16 SMR.
Yeah, I can tell you it's not as good. We are working on that. And the first idea is, what should we do? Should we first suppress the noise, pre-processing, or should we imply the noise suppression in the parameter estimation? So it's like in speech recognition. And it looks like we should first of all try to get rid of the background noise, and then it works quite good. Then your next question might be, what's about music? Yeah, it's not that good. If you have music there and music in the background, then the pure artificial bandwidth extension does not perform that well. But if we can transmit side information, it's like a codec, which spends not too many bits for the higher frequency band, and we know that the ear is not that sensitive there.
Another question is, okay, from the moment you switch from the traditional transportation to the pure digital, besides having errors in the bits of your transmitted data, which is less common in the digital networks, but then we face packet drops or packets arriving too late. And how eventually this is going to be resolved to keep the quality high even in certain packet drop rate?
Yeah. The steganographic transmission is not limited to bandwidth extension. You could use the capacity of 2 kilobits per second, for example, to transmit any information. And one interesting solution is to support packet substitution, to have redundant transmission. One of my students made some investigations in that direction, and that really helps to improve packet error concealment, but then we have spent this information, we will not use it for wideband. But it goes further, and from wideband we can extend to super wideband, and we have some capacity which could be used for packet error concealment.
More questions?
Mike.
I have a related question. That with the AMR codec, there are significant artifacts introduced by the codec itself. Presumably, the presence of these artifacts has the effect of concealing other problems, like channel errors or a poorly placed microphone or a poorly designed microphone. And then as we go to HD voice, those artifacts are going to be reduced, and the user may then become more aware of other problems, like a poorly placed microphone or channel errors or that kind of thing. Do you have some insight as to how the user's awareness is going to change, and how the irritation of other artifacts that used to be insignificant then becomes more detectable?
Yeah, that's a very interesting question. Let me say, if you are in a video audio conference, and one subscriber comes via the old telephone, you clearly see the significant difference between, and hear the difference between the audio quality of a subscriber A and the telephone quality of a subscriber B. But you need not to have such complicated constellations. In a normal telephone conference, which we have almost every day or quite often, we experience what is happening in the telephone network during the last 10 years. The telephone quality is not getting better, it's getting worse. And you know the people which are on the phone personally, and you clearly find out, oh, that's probably a mobile, and that's a terrible hand-speaking mobile phone, and that's a terrible desk telephone. In the office room, you hear the reverberation. I expect that the users are really aware of the degradations, and that we should do something, and that should be applied to the whole chain, and it starts at the acoustic front end. You address the microphones and the frequency responses. So we should improve that. We should not make them cheaper, but I'm realistic. I know we cannot replace all the devices we have there, so we should try to improve by intelligent signal processing, let me say intelligent equalization at the receiving end, or better pre-processing of a digital signal. I expect there is a lot room for improvement, even if we have there an AMR codec in between. Yeah? But I think this is a very interesting question for the near future.
More questions?
One question for a super wideband. You mentioned that would be an additional improvement, but I think what we found is that if you hold your cell phone like that, then the microphone is so far away from your mouth that actually the high frequencies are almost not being captured anymore. Do you do any studies on that?
Yeah, we have to distinguish between at least 3 different modes of usage. That is the normal handset mode, then we have the hands-free mode, and then we have the headset mode. And presumably you will not get all the improvements in each mode. If you have the headset, you clearly will get this improvement. Or if you have an audio conference situation with big loudspeakers. So that would be at least a fourth one.
A few years back, there were studies about artificial wideband extension, about user fatigue. Yeah. So sometimes you hear it for the first time, it's impressive, something's there that wasn't. But if you keep using it over the time, you may change your opinion. You may actually prefer a clean narrowband versus, artificially something. I'm not referring to the case where you embed information, but that extension is actually intelligently designed. But do you have any comments on that?
Yeah, there's a big test. It emerged from the LISTA project and the LISTA workshop last year, and there was a common effort to make a very deep comparison of different approaches of artificial bandwidth extension, and the results are very encouraging. If you would like to know more details about that, I could send you the paper. I don't have in mind where it was published. It is out meanwhile.
Let's thank again our speaker. Thank you, Peter.